We're looking at the Skywell vehicle here, and I'm going to point out a few features of the high voltage architecture now that we have the hood open and a few parts off, the aero fascia and all. Starting with the charge port on the side, we got DC and AC charge lines. The DC, they both come into this box. This is called a 3-in-1 box. It has the power distribution, it has the DC to DC converter, and it has the onboard charging control. So that's the 3-in-1 box. It's a kind of nice package up top, and it's basically the size of a shoebox. So the DC charge comes in here. These two cables go off to the battery, and these two high voltage cables go off to the inverter, and the inverter is the thing that turns the DC from the battery into AC to drive the motor. Over here, if you plug into a level 2 AC charging or level 1 charging, it comes in here and is converted to DC to charge the battery. So that's the onboard charger. Here we've got high voltage DC going to the AC compressor, which is mounted to the motor down below. And here we've got high voltage DC going into a little heater module. This is a resistance heater to provide heat for the cabin. And also, I think, heats the battery for cold days. 7 kilowatt DC charger. I'm sorry, heater. This thing on top is a electric vehicle charge controller. It communicates with the DC charger to let the charger know what voltage the vehicle's at, and so it can charge it at the right rate. And over here is the little computer, the vehicle computer, to control all of this. We've got a traditional 12-volt battery, and this cable right here is coming from the DC to DC converter to keep the battery charged. And that powers all of the accessories in the vehicle, the radio and the HVAC for the vehicle, and a traditional 12-volt fuse box right here. So all of this is nicely laid out. It's got unusual amount of package space and plenty of space. Most vehicles nowadays, this stuff is all crammed together, sometimes located in a package on top of the battery. The motor is water cooled and the inverter is water cooled, and the pumps to drive the water cooling are located down below there. We may get a better look at that once we get things torn apart. And there's a number of valves that direct the flow, either warm water from the heater back into the cabin heating, or cool water to cool the battery, or warm water to warm the battery, all controlled with these controlled valves up top. So the thermal control system is kind of nicely exposed and easy to see. I wanted to point out the anti-lock brake system. There's the master cylinder there, and down below it is the anti-lock brake system for modulating the brake in the event of when you have wheel slip. And one other thing that we can see is the chiller down here, which is a refrigerant to water heat exchanger bolted onto what would be called the firewall or the instrument panel. It's pretty wide open and easy to see. So this is just the basic elements that you have to make a electric vehicle work. Hi, welcome to Munro Live. I'm Paul Turnbull. We're here looking at the BYD motor that's for the Skywell. We're in the middle of a teardown here at Munro Associates. We're an engineering consulting firm, and one of the things that we do is tear down vehicles, look at the cost and how it's made for each component, and put that in a report and make that report available for sale. So it's one of the things that we do, and we're kind of in the middle of this, and I kind of want to show you how we go about tearing down motors and what we discover when we look at them. This particular motor, it is a BYD motor that Skywell purchased for this vehicle. So Skywell went to essentially a competitor and chose to purchase a motor. BYD today is making some of the most sophisticated electric motors in the market. This is not one of those motors. So this vehicle is from 2021, and so when it was being designed in 2019, Skywell went to BYD and asked them, do you guys have a motor? Obviously BYD is not going to give them the state-of-the-art motor that they had in 2019, but rather something they had on the shelf. So this kind of represents where BYD was about 10 years ago. And so it shows that how do you become one of the best car makers in the world and one of the best motor makers in the world? And the answer is you have to start here, and you got to get in production with things, and you got to get those lessons learned. And that's one of the things that's really nice as we take things apart and we see what they've done. Let me start over here with the rotor. This is the rotor and the stator. We call these the electromagnetically active parts. One of the first things you can recognize about it is they're relatively big and heavy for a 150 kilowatt motor. It's a little weird because if you take a 200 horsepower, that's 150 kilowatts. If you take the engine block of a 250 horsepower motor, a 200 horsepower motor, you wouldn't be able to lift it up. But if I compare this to other motors that were available at the time that this was designed, and so I've got one here. This is the Chevy Bolt motor, also 150 kilowatt motor. And I put it next to the BYD motor, and you can see that it's significantly shorter. So this is also 150 kilowatts. It actually produces more torque than this. This is 320 Newton meters of torque.
Loud noises!
So you can see that the Chevy Bolt motor, also 150 kilowatt motor, also an 8-pole motor, same voltage, but it's significantly shorter. This motor, when you take the electromagnetic active material, both the stator and rotor, is 5 kilograms lighter than this one for the same power and actually more torque. And there's other examples as well. This motor is competitive with the original Nissan Leaf motor from early 2000s. So it's not completely out of the neighborhood of motors, but it's at this point not competitive with the current state of the art. So that's one of the things that we first noticed, just the power and torque density. The other thing we noticed is the pattern of magnets in the rotor, and sort of notice how the pattern of magnets is quite similar to the Toyota Prius, which was also, one of the state-of-the-art motors back in the early 2000s when BYD was benchmarking and looking at how to make motors. They looked at good examples, and this is a great example of a motor, how to make a motor. And so they use a similar pattern for the arrangement of the magnets inside the motor. They also looked on the stator. We have the winding here. This is a traditional, what's called a stranded wound motor. And we did a video of that about a year ago on the differences between stranded and bar wound motors. The Chevy Bolt that I was showing earlier is an example of a bar wound motor. This type of winding has been done for almost 100 years. And the equipment to make it is much less expensive than a bar wound, the bar wound equipment. So if you're doing low volume, this type of winding is very competitive. But unfortunately, you just can't fit as much copper into the slot as with this type of winding as you can with a bar winding. And so you can never quite get the same efficiency and torque density with this type of winding. Although if you're good with it, then you can get some fairly competitive motors. And in fact, Tesla used this type of winding up until just a couple of years ago. So it's a good winding, especially for low volume motors. So this is what we first noticed from the electromagnetic portion of the motor. It's a solid motor, but not competitive from today's market. When I look at how this motor was cooled, it has this water jacket around the outside of it. So the stator is cooled. This stator is heat shrunk into this water jacket. The water jacket is made of an extruded aluminum part. Normally, extruded aluminum has the same cross-section from front to back. Here's an example from a Bosch motor, also a 150 kilowatt motor. And again, you can see that this motor is relatively long for this type of motor. And you can see that with an extruded frame, that you have these holes that pass all the way through. And so you need that for the cross-section in order to do the extruding process. This also looks like that on the inside, but then they've welded on caps and then machined it flat on both sides. So, and they've left just one opening here and one opening here. And the water goes in and then it goes back and forth and then comes out here. Normally, you would do this, send the water in, and you would use the castings on both sides to put the water channels in so you don't have to pay for this extra step of machining and welding in. And it looks to me like, in fact, BYD did exactly that, because here's the casting that this goes into, and I'll talk about the gears and bearings in a little bit. But on this side of the casting, we can see that they have the water channels cast into this part as if it had open channels on the extrusion. But then they welded on these parts, and so when they bolt it up, that's completely covered. And so this is an example of something you do when they originally made it like this. They counted on this RTV to make the seal, but then they discovered they had leaks. There was something in the process that was damaging the part as it was going in and forming a leak. And so in order to fix the leak, they welded it in, did the machining on this so that they could pressure test, leak test this part prior to assembly and make sure that absolutely there's zero chance of ever leaking. And it's the kind of thing that you only do after you've had some experience with water leaking into a stator. Obviously, if water leaks and it touches the windings, the water coolant is electrically conductive and you have a bad day. So that's a serious issue, and it's something that you just absolutely can't allow to happen. And this is how BYD made the change to eliminate that failure mode. We have a similar kind of story of lessons learned with the gears and bearings. So one thing I like to do on all these is just give it a spin to see just a feel for how much friction there is in the system. And this one has the normal amount of friction, typical of what you'd see even with a internal combustion engine gear set. It has low friction, but not so low that it doesn't immediately stop when you try to spin it. The other thing we look at, this is a relatively compact and small gear train. The reason you can do that is because the motor only produces 320 Newton meters of torque, and so there isn't a huge amount of torque necessary, so that each gear can be a little bit lighter and smaller, which is nice. It's using ball bearings for the motor shaft. This is the input shaft, and the lay shaft, but then tapered roller bearings for the differential. Here we have the input shaft, the lay shaft, and the differential. Here on the input shaft, the motor comes in with a spline coupling into this back side here. The motor is supported on its own two bearings. And then we have this input shaft also supported on two bearings. So that allows for the motor shaft and the input shaft to be slightly misaligned, but so normal manufacturing tolerances, but still work fine. So that's kind of nice, and it makes this an entirely separate unit. Some manufacturers build this gear right onto the end of the motor shaft, and that helps them eliminate one of the bearings, either this bearing or the bearing that's on the motor shaft. So it can be done a little bit less expensive. In this case, they choose to have a separate input shaft, and it simplifies assembly. But speaking of assembly, there is a little bit of an issue. This bearing, the outer race of this bearing, has to somehow be clamped in a way so that it won't spin. And the way they do that is with this bearing retainer plate. Now, bearing retainer plates are used in alternator construction and other bearing applications as a tried and true method of retaining a bearing.
Oh, come on!
So this is a bearing retainer plate, and the way that you have to assemble this is when this part comes on, then you run 3 bolts in, and these 3 bolts have to pick up that bearing retainer plate and draw it in to pull the bearing into the pocket. The only trouble is that this is a blind assembly operation. When you put this bolt in, that bolt has to find that bearing retainer plate. You can't reach in with your hand or some other thing to get the bolt started. So you have to use, in your fixture, some sort of spring-loaded pin to pick up these 3 points and locate it so that the bolt will find the hole as you're putting it together. That does work, so assembly is possible, but you never can be certain that the bolt didn't cross thread or just slightly misalign on the thread as you're putting it in. And so once it's all together, you can't see, hopefully you miss it clean and it doesn't work at all, and that you can tell right away that it's misassembled. Unfortunately, sometimes you catch it, it does cross thread, you catch it, and it works just fine for a little while. Eventually, though, the cross-threaded bolt will give way, and then this bearing retainer plate will fall out of position, touch the spinning gear, and then you've got a bad problem. Either a horrible noise, or worse, it can actually lock the gear such that the front wheels of the car lock up without warning. So not a failure mode that's acceptable. And so I suspect that this method for retaining the front bearing is not something that BYD is still doing in production. I want to show, at the risk of plugging Tesla again, I want to show just another example of how companies address this issue. So this is the same bearing in a Tesla drive unit. It fits right here on the lay shaft of the Tesla drive unit. And it has this little notch in it. And that little notch engages with a spring-loaded pin. So it can be located anywhere. And the spring-loaded pin comes as we just push it in, and this has a slip fit into the housing. So it fits into the housing very nicely. Assembly goes easy. And then as you start to spin the motor, this outer race isn't going to stay still. It'll eventually rotate until it finds that spring-loaded pin, and it'll snap into place and keep the outer race from spinning. So now it's fully located, both on the diameter from the hot casting, and it's kept from spinning by that little spring pin. So this makes assembly extremely easy. It's a blind assembly, but you don't have to catch a threaded fastener from the outside. So that's just another way that companies are looking at managing this rather difficult assembly process. Okay, so the gear, that's an 11.2 to 1 gear ratio. And we do, as we tear things apart, benchmark and look at the cost of every component, these bearings, the gears, every fastener, weigh everything, and have photos of every component. So that's one of the things that we're able to offer as we go through our teardowns. When it comes to the inverter, first thing we notice is on the inverter is that it's in this big cast aluminum box. So we have a drive unit that has big cast aluminum housing, and we have a separate cast aluminum box for the inverter. What modern drive units are doing is they cast this lower box right into the housing that holds the motor, and that ends up saving some money. And then this cast aluminum cover, which is also kind of expensive, can become a stamped part. And that's also a way to save money on inverters. This is kind of an old school inverter where I kind of like the way it goes together because it's so understandable. And so I wanted to show you how this works because each component is separate. Today, most inverters are highly integrated. So this part is the control board. It's essentially a computer. This is the processor. It's got memory. This is the thing that makes the decisions, that does the control for the motor. And what it controls is, this is the three-phase connector. This has, in this case, just 2 current sensors, which is a way to save money. Normally, companies are using 3 current sensors. So this is an example of inexpensive inverter. The thing that the control board controls is this, which is the switches. They're IGBTs, that's integrated gate bipolar transistors. They are switches that turn on and off the current from the DC battery. So the DC current from the battery comes in, and this switches it and turns it into three-phase AC. And I'd like to do a video just on how this component works, how do you switch DC current and turn it into AC. The circuit board on top is called a gate driver, and there's 6 individual parts of this circuit board, all repeated, and each one drives one of the 6 switches inside this. So underneath this circuit board is one of these, which is a Infineon hybrid pack that has the 6 switches built inside one box, one package, and the package has with it the integrated cooling for the switches. So when you're passing 500 amps through this thing, these are very small switches, and the current passing through the silicon produces a conduction loss, which produces heat. And every time you turn the switch on and off, you get a little bit of loss. And so switching loss and conduction loss is producing enough heat that we need to keep this cool with running coolant through it. Infineon's been making these for years, and there are now a couple of strong competitors in the market that are making identical products. And because of that, Infineon is, their prices have come down dramatically. So buying just a straightforward package of all your 6 switches makes the inverter much less expensive and easier to integrate. This big black box here is the capacitor. So it's a large capacitor. What this does is when you turn the DC into AC with a bunch of discrete switches, you end up creating current ripple, both in the AC and on the DC side. And the capacitor absorbs that current ripple and smooths it out. It also is something that can deliver a gigantic amount of energy very quickly. And so when you turn a switch on, you can deliver that energy to the motor much faster than a battery can. And so this is like a little battery that stores some of the energy from the battery and can deliver it and accept it from the motor very quickly, and then meter it out back to the battery at a pace that the battery can absorb it or deliver it. So this part of the component smooths out that power flow between the motor and the battery. It also has, by the way, this part here is a filter. It's a ferrite filter that provides even further smoothing of that ripple caused by the switching. So this is a pretty sophisticated inverter for its time. Again, probably designed 10 years ago. In production for about 3 years or so before BYD sold it to Skywell. And so they've moved beyond this, and BYD now has some of the most sophisticated inverters and motors in the world. Absolutely love to get our hands on one of the new ones. If anyone from BYD is watching, that would be awesome. We'd love to do a video on that. But this is where they started. 10 years ago, they started this, got into production, and were making competent electric machines. And they've only gone from this point, on to much better products, where they've taken the lessons learned that we can see in the parts and built them into their next and third generation products. So this represents kind of a first generation for BYD. And really excited actually to see what they're doing next. So that's what we have today for you on Munro Live. Thanks for tuning in. Really appreciate the audience here. And we'll talk to you again next time.